All right, so when we left off from here, we were talking about the compiler package. Get back into that mindset. So the compiler package compiles bytecode, functions into bytecode. By default, packages that you install are not bytecode compiled. There are some exceptions, some things that come with R, the so-called base packages, which include base, stats, some of the graphics stack, and recommended packages like mass and matrix. Those are bytecode compiled by default as of, I think, R214. Certainly they are bytecode compiled by default now. But if you write your own package, by default it's not. You sort of have to go out of your way, and there are various ways to go out of your way to do that. The downsides to using the bytecode compiler, package compiler, it will have a bigger install size, not by much, but it will be larger, and a longer install process, again, not by much, but it will be longer. These are the kind of things that, when you submit to CRAN, you may have a very grumpy person ask you why you're bytecode compiling or something, but there's no real downside these days. The upside is you can expect faster code. How fast? Again, maybe 2 to 5% faster. 5 is sort of best case. So how does it work, right? You can compile functions themselves very easily. So if you have a function, we're going to take x and add 1 to it, just some dumb little thing. If I print that function, just say test with no evaluation, it'll print the function. That's what we see. And it's important to note that's what we see. If we load the compiler package, library compiler, and replace test with cmpfun, which is from the compiler package on test, print it, we see our source code and also the bytecode address. So this is how we know it has indeed been bytecode compiled. You can disassemble. This is a function from the compiler package. If you disassemble, you will get an idea of what the bytecode looks like. It's a bunch of unreadable gibberish, but you can see it's actually doing what it claims to be doing. If you are compiling a package, so this sort of assumes that you're using Linux. If you're using Windows or Mac, you're downloading binaries, which have been compiled for you. And there you just sort of have to take what you're given, I believe. On Linux, you can pass install options, -- byte compile. Possibly with type equal source on another platform, that would work. I'm actually not sure. I have not used Windows in a long time, unfortunately, or fortunately, depending on your point of view. From the shell, if you're installing a package, and this is true for any platform, if you're building a package from source, assuming you're in like Bash, not some weirdo who uses C shell or something, you say export R compile packages equal 1. Then when you rcmd install, it will bytecode compile the package. C shell people use env, I think. I don't remember. But making sure that your package is compiled, say you ship it off to CRAN and you want everybody to have your package compiled, in your package there's a description file. In that file there's all kinds of things you can put in. One of them is byte compile yes, no. And it does what it says it does. If you say byte compile yes, then by default, whenever it's built, it will be bytecode compiled with the compiler. That is overridden by no byte compile. Just nice to know. I wouldn't recommend turning this on during development if you're doing a lot of rapid installations and then checking and things. It's not a lot of extra time, but it's like maybe a couple seconds, which is enough to annoy me. CRAN may yell at you. Probably not these days, but they yell at you for everything. So it's likely to happen at some point. So there's another kind of compiler, the one we talked about first, right? We can actually utilize machine code, all right, from a foreign compiled language like C or C++ or Fortran. Probably the most popular way people do that today is with the RCBP ecosystem. We'll talk about that on Tuesday. It's difficult. Using the compiler package in R is very simple. It's free. Free speed up, I mean, you don't have to work for it. It's basically just there. It just sort of works very easily. But it is it's not that great. Whereas utilizing machine code is very, very, very compelling from a performance perspective, but is much harder to actually use in the first place. But we will be talking about how you would do that with RCPP on Tuesday. For extra credit, you could evaluate these two things here. We're returning to this transpose thing, remember from the beginning, where we transpose inside the loop or before it. You can actually compile these with the bytecode compiler, CMP Fun, and you can look at the bytecode with disassemble and see what it's doing. If you do that, you should be able to convince yourself that it really is still transposing each time inside the loop, even with the bytecode compiler. So the compiler does not make bad code good. It makes any code slightly faster, but it's not on the same order as a machine code compiler with optimization. Okay? So compiling R with a different compiler can improve performance, but doing so is not entirely trivial. It takes some work. I would recommend looking at that website that Intel provides. It's very useful. The compiler package is, like I say, free speed up. You don't even have to work for it. It's just there. But it's small. Works best on loops. And for really good speed up in serial, that's where we still are for the moment, then moving to compiled machine code is still the best. Any questions so far before we get to parallelism? Okay. So about parallelism, we're still in broad overviews, right? We haven't gotten to very specific things yet, and we won't get to anything too specific this time. Tomorrow there's a session we'll do on using R with MPI libraries, and we'll have some real applications as examples. Here, again, broad overviews. This is probably everybody is not surprised. You know, serial programming, you're just, for example, using one CPU, parallel, you split it into subproblems and utilize multiple CPUs. CPU is a very abstract concept here, and is getting even weirder all the time as these new kinds of coprocessors are invented. But you're utilizing more hardware, let's say. And so this is the graphic I like to give, which shows in serial, well, if you want to make a peanut butter jelly sandwich, well, you might, you gather your resources, you do all that as one step. You make the peanut butter side, the jelly side, you put it together, you're done. In parallel, well, you got to split this thing in two, and so you farm this work off to grad student 1 and this to grad student 2, and then they have to checkpoint, they have to get together and make sure that one of them didn't put nails on one or something stupid, and then you put the thing together and you have your sandwich, right? So a little bit of terminology that we just throw around a lot when we talk about parallel programming. Some of this you've probably seen, some you may not have. Implicit parallelism is exactly what it sounds like. So the details are hidden. It's free in the way that I keep using the term free. Explicit parallelism, you got to get your hands dirty. Batteries are not included. Embarrassingly parallel or loosely coupled. You may have heard this one. Maybe less people have heard this one, I would guess. So in an embarrassingly parallel problem, it's sort of obvious. It's embarrassing how easy it is to make the thing run in parallel, right? Or loosely coupled. There's a lot of independence. There's not a lot of coupling in the problem. The opposite of this is tightly coupled. So a problem is tightly coupled if it's not embarrassingly parallel. There's not a lot of independence. You really have to work hard and think hard to figure out how you're going to get this stuff to run in parallel. So as examples, you could imagine you have two different kinds of models you want to fit. We saw some models in the last session. I'm not saying from a computational standpoint this is a good idea, but you could fit one on one core, one on the other, and theoretically it would be faster, right? That's an embarrassingly parallel problem because there's no interdependence. You just fire them off and things work fine. A tightly coupled problem would be like, imagine you had one really massive model you want to fit, and you want to speed up the evaluation, the fitting of that one massive model on massive data. That's much harder, and you have to work much harder, and a lot of the parallel R tools are not suitable for that kind of problem. Most of the simple parallel R tools are really more living in this territory and really living in shared memory. So talking about speed up, we talked about wall clock time at one point. What is it? The time of the clock on the wall from start to finish. It's a very useful, sorry? Oh, sorry. Yeah, speak up if you have a question.
So you were on vocabulary.
Sure.
So one of the things that I really struggle with vocabulary, they're sometimes used interchangeably. Can you try to distill the difference between nodes, cores, and processors, and which one we're running on? So like you have a cluster, clusters are made of nodes are made of cores are made of processors. When we think of R as being single-threaded, that's single-threaded on processors, which are inside of nodes, which are inside of cores. Is that right?
That sounded close. So, and maybe it just went by too fast. But this is an interesting point, and it's hard to do. And now that you mention it, I should have had a picture, and I'm sorry I don't. But the question is the distinction between nodes and cores and maybe threads and processors. What is the difference? So it's a very good question. So when we get to some hardware specifically, point at me, and we'll come back to this because I have almost a good diagram. It'll make it slightly more real. But wall clock time of the clock on the wall, speed up. You probably know what this is. You measure one thing, you divide by the other. The initial one is usually taken to be at 1 core. What is that? We'll return just shortly, I promise. Good speed up looks something like this. The blue here is the theoretical maximum. You can actually dip over that line, and I have an example where we will do that. But generally, you're living down here. The way you dip over the theoretical maximum is by really understanding how the cache interacts with your problem. It's not something that is maybe common or typical, but it can happen. Bad speed up would look something like this. You're throwing more cores at a problem, and it's really not getting any faster. OK, so this is almost the kind of diagram we would want. Here I'm still using CPU as a very abstract thing. In shared memory, like on your laptop, your desktop, you can directly interact with memory across different computing units. Okay? So like on your laptop, you probably have one physical CPU. That physical CPU is made up of cores. Those cores are kind of hard to define, but let's just call them computing units. And they behave like CPUs of 10 years ago. Okay? And there are physical cores and logical cores. Physical cores are the things that sort of behave like processors from 10 years ago. Logical cores are these strange things you do with so-called hyperthreading, which is usually a big fraud, a big sham, but sometimes can be beneficial, maybe deeper than we want to go. If you go to so-called distributed computing, you're making up sort of a mega computer out of multiple shared memory, we call them at that point nodes. So here we have one node, and it has its own memory and its own processing units. That CPU may in fact be several CPUs. There may even be a GPU attached on. It may get really weird. But you would have this shared memory piece. It can work on its memory, but it can't work on the memory of the stuff over here. So to work from this node to this node, you have to go across some kind of interconnect. That interconnect could just be regular old Ethernet if you're unlucky, if you have a lot of money to throw around. There's InfiniBand. SGI is a company, and Cray is a company that basically makes their living making really fast interconnects. And basically, it just allows you to indirectly modify the memory on another node. So you have, in distributed land, you have one big machine. That machine is made up of nodes. Each one of those nodes is really, think of it like a bunch of laptops chained together over a network. So like, well, that's a bad example, but yes, it's a bad example. So if you think of like one big machine made up of multiple shared memory nodes, within a node you have maybe 1 or 2 physical processors, or maybe up to 4. I think 6 is maybe really pushing it. Physical processors, each one of those has multiple cores on it. That's where your computing is going on. A little convoluted. I will try to remember this and come up with a better picture and bring this up again tomorrow. Hopefully that at least begins to broach the subject. It's not entirely trivial to make that distinction. And it gets really weird when you have like GPU coprocessors, Intel Xeon Phi coprocessors in the future. If you know what the Intel Xeon Phi is, eventually there will be computers with, on a node, you have several, and instead of a regular CPU, you'll have several Xeon Phis. So the landscape is going to be really weird, but sure. So you have probably one physical thing you plug in a socket, right? Yes.
So you don't need that. You say there are 4 CPUs.
I'm using the word CPU here very abstractly. Probably these are cores. You may be living on like a server. On a server, it's not uncommon to have multiple physical things plugged into sockets, right? Each one of those would have multiple cores, right? I really do apologize for not having a better graphic. I will try to bring one tomorrow, but it's a little convoluted. So these are 2 supercomputers owned by the University of Tennessee. The one on the left is a shared memory machine. So it has 1,024 shared memory cores. So you could, if you're familiar with MCL apply, you could fire off MCL apply, n cores equal 1,024. Probably you'd need a very specialized problem for that to scale well, but you could do it. Has 4 terabytes of RAM. Neat computers made by SGI. Kraken is a Cray machine, has 113,000 cores, and total of 147 terabytes of RAM. So shared memory machines don't get a whole lot bigger than this. It's about as big as shared memory machines get. I think they have upwards of 4,000 cores as the biggest at this point. There's like a physical limitation. On distributed memory machines, you could go bigger, but all kinds of problems happen. These kinds of architectures are sort of in transition at the moment and getting weird, as I've hinted. But for shared memory computing, you can only really go so big. Distributed memory, you can really go astronomically huge, but these are harder to use. So that's sort of the trade-off. In R, there are packages for dealing with all of these things. So for shared memory machines like your laptop, like a single node of a server or even supercomputer, you have the parallel package, which has been around since I think R211 or so, is a recommended package. There's Snow, multi-cores not there, for each GPU tools if you have a GPU, HypLarm if you have access to a GPU, does linear algebra on a GPU. Distributed stuff, and in fact you could say and many more. Here in distributed you would say these and a few more maybe. There's PBDR, the stuff that I work on and others work on. There's RMPI. We'll talk a little bit about RMPI today and a lot about PBDR tomorrow. There's R Hadoop from Revolution Analytics. That is an ecosystem of packages for using R and Hadoop together. There's also Repay, which is another system for using R with Hadoop. Depending on your problem, Hadoop may be a good solution, may not be. We won't get into that. The CRAN HPC task view is very useful. If you check out the high performance computing task view, you'll see all the packages that get lumped into high performance computing. There are several hundred that I have not mentioned. So there's lots of good stuff there. I want to talk just for a moment about the BLAS. So BLAS is basic linear algebra subprograms. And these are the core simple linear algebra arithmetic operations. So vector, vector, matrix, vector, matrix, matrix operations. R uses BLAS and its extension LAPACK for most linear algebra operations, not all, if you could believe it. See me later if you're curious. I could talk quite a bit about linear algebra in R, but probably it's not a good thing to bring up at parties, let's say. But so there are different implementations of the BLAS. These implementations will have massive, profound impacts on performance, and these are all free. So the performance change is free. Not all BLAS implementations are free. We need to draw that point very clearly. There are even multi-threaded BLAS libraries where you can get shared memory parallelism for free, and it's not very hard. Now here's a little thing I ran on my laptop. Okay, So the benchmark that I'm running, I generate some data. The data size will differ. This is just the first one that you see here. It's just random data, 2000 by 2000 matrix. I compute, so I use our benchmark. I compute x times x and the SVD of x. And I do this with different implementations of the BLAS on my laptop. So here, x times x on a 2000 by 2000 matrix, that's roughly 31 megabytes of data. So this, so here I'm showing the average wall clock time for 10 runs. Lower is better. So this is the so-called reference BLAS. This is probably what comes with R if you're downloading a binary on Windows or Mac. On Linux, it gets more complicated for downloading binaries. But this is the reference BLAS. You see, reference BLAS really does the worst. Okay, it's not good to use that, but that's what ships in the source code with R. You could use a different one. For example, this is Atlas, the second one here. Atlas does a whole heck of a lot better than reference BLAS, and it's free. It's open source, so free as in speech. If I put on my Richard Stallman beard for a second. We also have the open BLAS. Now here I say open BLAS 1. That means with one thread. Okay. Open BLAS 2 means with two threads. So open BLAS is really crushing the competition, and it's multi-threaded. And it uses OpenMP. So you say export OMP num threads 2 or whatever, and automatically it's just going to farm off that work for you. It is worth noting, however, that at least in Debian, and I've extensively tested this in Debian, Ubuntu, Mint, and all these derivatives. It's the same thing, basically. Open BLAS causes all kinds of problems with the parallel package, specifically with forking. Anything that calls system fork is going to misbehave with open BLAS. So that's something to be aware of. At the very least, you could use Atlas. Atlas is a whole heck of a lot better than the reference BLAS. It's single-threaded, but you know, if you are not using the parallel package or forking, let's say, in particular, then you can just go ahead and use open BLAS, and it's very fast. There are other implementations. MKL is probably the most famous commercial one from Intel. MKL is crazy fast. It is also multi-threaded through OpenMP. And I mean, it would just be like, take this and move it over here, and that's probably what MKL would look like on Intel hardware. It's very, very, very fast, but it is commercial, and you have to pay for it, several $100s at least. It's cheaper than the compilers. Anyway, there's a lot you could say about linear algebra. It's exciting. But okay, so I mentioned that using open BLAS on Debian and its derivatives, so using the software repository apt-get install libopenblas-dev, that will install it for you. Then you can change which one R will use through update alternatives, and just pass --config libblas.so.3. It will bring up a little interactive incursus thing, and you can choose which one you want. Yeah.
How can you find out what it's using right now?
How can you find out what it's using right now? Assuming you're using a Debian system, I've tested this extensively on Ubuntu, and yeah, my Debian server. So yeah, if you run this, then that will open a little interactive incursus thing. It's not incursus. It just opens a little interactive thing, and it will show you the one you're currently using and list the options that you have available. So, for example, if you were to SSH into that server we have running, using the exact same user and password that you use to log into RStudio, if you SSH in there, you're not in sudo, but maybe this will work, or maybe not. But I could show you anyway. So like, oh well, I have to. libblas.so.3. Okay, so this is what it looks like. So right now, I'm using Atlas. The reason I'm using Atlas is because I was using Parallel, and I don't want seg faults everywhere, which is what would happen if I were to use libopenblas. So it asked me, press enter to keep the current, or choose a number. So This is the reference BLAS. It's terrible, don't use it. This is Atlas, and then those are open BLAS, so I'll just do that.
Does anybody know why that's the reference?
Why it's called reference?
Why is it
So it was the first one. So it's the reference BLAS because, like, imagine you wanted to implement your own BLAS. This is what it should do. It's your reference, right? You can tune it and do all kinds of cheating and make it faster on different hardware, but it has to solve the same problem with the same result. Okay. And just for kicks, the BLAS were developed by some people right down the hall. That's sort of interesting. Yeah.
So when you say it doesn't do well with a parallel package, does it do fine with like Snow and the other packages?
It should. It should. So we'll get to specifically why that is, but the basic answer is it doesn't play well with fork. I don't know why it doesn't, but I know that it doesn't. So if you're using, for example, Snow, if you're using the Snow components of the parallel package, that should be fine. So if you're using sockets, that should be fine. But if you're using MCL apply, that will cause seg faults. And I don't know why. I just know that it does it. It's completely replicatable. OK. So parallelism, it requires independence. We've talked briefly about this. Separate evaluations of R functions are embarrassingly parallel because R is a quasi-functional language. Functions don't have side effects. So if you change data, you're actually creating a copy and making changes in the copy. So it's really, really easy to do multiple evaluations of a function in parallel. You don't have to worry about global values unless you really go out of your way. It is possible, but generally that's not how people do things. As I say, I'm not a biologist, but I try real hard. For biological applications, maybe it makes sense to split by the gene, or you're fitting like multiple genomes or something. I don't really know what a gene is. Maybe somebody could tell me. But I read the definition, but I think like with linear algebra. So portability. Not all the packages that I mentioned are available on all operating systems, and for any kind of HPC application, usually that means doesn't work on Windows and works elsewhere. So Windows is a funny animal. In the desktop world, obviously it's king, but in high performance computing, it is always the thing that just breaks and is annoying. And some things just will not work on it for various reasons, as we will see. Random number generation parallel, just say be careful. There are various packages for helping with this kind of thing. You want to make sure you have good independent random number streams. The R-Lecoyer package is probably the most popular. R-Spring exists. Do RNG if you're living in for each land. We'll see how that works. R-Lecoyer very useful when you're working with MPI. We'll see a very direct application of that tomorrow. So summary, there are many kinds of parallelism available to R. Some are easier to utilize than others. A better BLAS is free speed up for linear algebra, but is not necessarily trivial to do. I only know how to do it in Linux. I assume there's an easy way to do this on a Mac. On Windows, I have no idea what those people do. But you could ask Wei Chen. He would probably know. Wei Chen is, raise your hand. So if you work in Windows, that guy knows more about Windows than people outside, than just about anybody outside of Redmond. So at least for HPC and R. So okay, any questions before moving on to some simple direct applications? All right. So shared memory parallelism in R. Okay, so parallel package comes with R as of 2.14.0. You would really have to go out of your way to not get it. It includes all of the components of multicore and some other ones that are actually really nice, and most of the Snow package. It does not include the ability, I believe it is still true, that it does not include the ability to use RMPI, for example. So if you wanted that kind of thing, you would still need the actual Snow package. And so as such, I say it has two disjoint interfaces. It's combining these two things. The reason why it's combining them is because multicore will not work on Windows, because it uses a system fork. Windows doesn't have one. And so therefore, if you're doing if you're using the parallel package and you're worried about platform independence, you would want to live over here. So the parallel package operates on a fork join paradigm, which is pretty much what it sounds like. So if you're doing stuff inside of there in parallel, you fork the R process, which creates some other R processes. It will copy data on write that is managed by the operating system and is fairly efficient. If you're not modifying data, no copy will take place between the forks. Then it will, when they're done, they'll join up and go back to the original. So data copied to child to any of the children on write. This is again handled by the operating system. You don't have to worry about any of it. It's very efficient. So it's not as efficient as threads, but it's very efficient and is the most efficient thing easily available to R. It has no Windows support, however. So this is the reference for the function. So what is MCL apply? MCL apply is the multi-core lapply. This is why I say if you can think in terms of the lapply, then it's very convenient for parallelism because it's just so trivial to turn an lapply into an MCL apply. You set mc.cores equal to, this is the default, you change it to whatever you want. It has some things for handling random number generation, prescheduling. And so, for example, you say lapply 1 to 10 square root. What does that do? Forms the vector 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, applies square root to all of those values, returns that in a list. MCL apply does the exact same thing, but on multiple forks. So assuming you have the actual cores available, it will schedule to multiple cores, and that scheduling is handled by the operating system. And then you could see, do they do the same thing? They do, right? So here, in the multi-core side of things, you could, for example, say, oh, I see what I'm doing. OK, I forgot I did this example. OK, so to illustrate the point about the mapping between cores and actual processes. So I did this on a machine with 2 cores. And I said I had 4. And then I say sys.getPID for my function. And I do 10 of them. So what is going to be the process ID of this? So at each evaluation in my vector 1 to 10, what is the PID? So we have 274 and then, or 2745 and then 2, 3, 4, 5, 2, 3, 4, 5, 2, 3. Okay? So if I tell it I have more cores than I have, it doesn't care. It's going to spawn that many children to do the computing on. And you see there are these 4 here, and it's just sort of passing work around as it needs to. But there's no direct mapping between my actual hardware and what I tell it to do. It's just going to do what I tell it to do, which is actually nice. If we wanted to use the number of cores available on the node, then we could use the detect cores function. But and here, for example, if I give it less work than there are resources it thinks are available, then it's just going to use up the resources as it needs to. The Snow side of things, Snow uses sockets. Okay, the plus side is this will work on all platforms. So you write code on your Windows machine, it'll run up on your server or the cloud or wherever. It's more fiddly than MCL apply, and it's not as efficient as forking, but it's fine. The way this works, as I say, is a little more fiddly. You say make cluster, and you store this somewhere. Usually they just call it CL, just to show there's no semantic meaning. I call it my.cl. Make cluster detect cores. So we want however many cores are on the system. I think I ran this on, I ran this on my laptop, which has, the laptop thinks 4 cores. It has 2 physical, 2 logical. So it will detect, if your operating system thinks hyperthreads are cores, then so will R. So we make the cluster, it stores this information. We could say, for example, par sapply, sort of the equivalent of MCL apply over here, on the cluster, on the data, apply square root, same thing as before. If we want to kill the cluster, we say stop cluster on the name of the cluster.
So I have a couple questions.
Sure, yeah.
In my lab, this is always what we do.
Sure.
So we use this setup.
Sure.
So 3 questions, Dennis.
Okay.
And anyone stop me if I'm asking too many questions. I'm the only person here apparently on this question. One is, when is it appropriate to make more children than you have actual cores? So normally
Sure.
what you do is you think, oh, I have 30 slots, I should just make 30 processes, and if there's more than 30 tasks, it'll just loop back through.
Mhm.
And what we usually do is just say, okay, if there's enough memory to run on one, then by extension there should be 30 can run on 30. When would it be appropriate to run 60 on 30?
So that may not be true, because there may be copying going on.
Mm-hmm.
And you may actually blow up your memory where it would run on one very slowly. But if you were to, for example, run, you have 30 cores, let's say. One core may run so it may run on one core just fine, but with 30 it may not, because you may just end up copying the data too much and just use up all your resources. Maybe not. It really is problem dependent.
No, I know, and I'm just saying, so it's the memory, which what you're harping to there is the memory, the copying. So
yes.
So basically, if so for people who know what I'm talking about, if you hit Control-Delete right now, if you're on Windows and you go to the performance, and you see literally how many panes are. That would tell you something about hyperthreading or available number of cores on your laptop. You can do it if you're in Windows right now, and most of you probably have a laptop. You see 4. So you could make cluster. You could make 4 of them, and you could say, okay, I want 4 tasks and distribute those 4 tasks. I'm just wondering when I'm allowed to do 8.
You're always allowed to tell it that you have more resources than you have. When is it computationally beneficial to do so? So it is problem dependent. I have done this in the past. Off the top of my head, what would be a good example of?
Like when one would finish way ahead of the others.
Yeah. So if you imagine a scenario like say you're fitting a bunch of ARIMA models. This is something I have some experience with. What is an ARIMA model? It's like a time series model. It doesn't matter. So when you're fitting ARIMA models, you have a lot of tweaking on the parameters, basically. You could say, I want 0, 1, 2, 3 for some number, and there are 6 of them. And so when the numbers are smaller, they finish much faster. So if you were to divvy up the work in such a way that all the high numbers were on one core and then all the lower numbers were spread out among your remaining, that would be a very bad work balance. And so in that kind of case, it might be better to tell it you had twice as much resources available, compute resources, than you actually had. It really is problem dependent. It's hard to say in general at the moment for me. That's an idea.
Stupider question, which was, I say the word all the time, but I have no idea what it means. What literally does sock mean? Because you left an actual argument out of that thing, which will run, but it's taking in a default, which is make cluster is actually a general function.
Oh, this one, yeah.
Make sock cluster or make MPI
Sure,
cluster.
sure.
And I don't actually know when something's defined as a sock, because I thought it was just on the laptop, but it turns out you can do it for clusters too.
Mm-hmm.
What does sock actually mean?
Sock is just short for socket. So it's a socket connection.
Well, when does it count as a socket? It just, like, when does something... I'm really up to like 12 on this question. So like, when would you be using a socket connection versus something else? Is it always assumed that that's the...
So when would you be using a socket as opposed to something else within the context of like make cluster?
Yeah.
Okay. So by default, when you just say make cluster and then I have 3 cores, let's say, or whatever, it's going to use sockets. And in fact, in parallel, you're fairly limited. If you're using Snow, if this is the make cluster from Snow, you could set up, assuming you had all the right packages and stuff installed, you could set up MPI clusters, right? I'm not sure if that answers the question.
No, it does. It's just sort of thinking about when these things, because there's a bunch of arguments that are sitting sort of hidden, invisible in the
Sure, sure. And now, to bring up the point, when would you want to use MPI cluster versus this? This is probably a better way to go with sockets, assuming you can't use forks. then sockets are a good way to go when you are working on a shared memory resource. If you want to utilize multiple nodes, then you got to use MPI, pretty much. So, okay. So I think that kind of answers, hopefully. Do ask questions, though. I do appreciate questions. You know, I think these are great questions. I really do. So keep them coming. So then stop cluster closes the socket connection, and then you're done. Just a very quick summary for these things. Detect cores. This is a useful thing for anything in the parallel package, whether you're using the Snow side or the multi-core side. Split indices is a helpful little function for if you want to divvy up tasks. It's just sort of a convenience routine. It's not actually having anything to do with the hardware or anything. On the multi-core side, you have MCL apply, MCM apply. M apply is the multivariate L apply. MC parallel and MC collect are really cool, and I never see people use them, and it makes me so sad because it's just a really simple way to do fork exec from R. If you're familiar with like C programming, it's just such a trivial way to do fork exec. It's so cool. So those are there, and they're really fun, and you can do some really interesting things with them. With Snow, you've got make cluster, stop cluster. Those are sort of the beginning end. Par L apply, par S apply, and there are many others for both of these. But these are the ones that instantly pop into my head when I think about what I want to do with these pieces. Okay. There's also the for each package, which has been billed as one ring to rule them all, but I disagree to some degree, and we'll see why. It's on Krans from Revolution Analytics. The main package is for each, and it forms its own ecosystem where it defines a single interface for a bunch of back-end packages. The back-ends, as of right now, are doMC, which is the multi-core package, doMPI, which would use RMPI, doParallel, which uses the parallel package, doRedis, which uses some kind of Redis interface. I don't really know how that works, to be honest. doRNG, which uses, I think, RLacoyer, and doSnow, which uses Snow. Okay, so it defines a single interface, and you say, well, on my laptop, I don't have access to fork. I can't use multi-core. So what I'll do is I'll use for each, and I'll use doSnow on my lap, or do parallel on my laptop, and which is running Windows in this experiment. And I'll debug it and test it there, figure out how it works. When I go to my compute resource, my server, I'll use the doMC or the other side of doParallel. And we'll use forks, and it should be a little bit faster. So 99% of the time, you can do that with for each, and it's fine. But there is an issue I would like to bring up. So it works on all platforms with the correct backend. Not all backends work on all platforms. So doMC is not going to work on Windows. But there is a backend which will work across all platforms. It can even work in serial with a very minor notational change. I don't know why you'd want to, but you could. The idea is you write the R code once, use whichever backend you prefer. Maybe you run out of resources on your shared memory node and you want to scale up using MPI. You could. And 99% of the time, it's great. One thing I don't like about it, it has really bizarre, non-R-ish syntax. Somebody who I think didn't really appreciate R cooked this thing up. And then it has some strange efficiency issues. What do I mean? So this is a log scale plot of runtime in seconds. Here, the blue is for each, so lower is better. Green is MCL apply, red is L apply. And the length, this is the length of the iterating set. And what I'm doing is a really, really trivial operation. That's important. So when I do for each, we haven't talked about the syntax just yet, but here it is. For each I equal 1 to some number of things, percent do par percent, tiny fun. Okay? That function is really, really, really quick to execute and return. That's important. In that case, for each is going to take way more time than a serial run, like several hours more. I don't know why this is. I test this every now and then. It's still broken as far as I'm concerned. The slowdown appears to occur in the iterators package, which is a dependence of this. I emailed the maintainer of the iterators package. They basically said, thank you very much. It's open source. Please consider contributing. They haven't fixed it. Now, if your function is not tiny fun, okay, if it really is doing stuff, for each is great. It's fine. But you really need to understand that if it's like square root. And it sort of bugs me because their canonical example is this with tiny fun equal to square root. And it's outrageously slow. It kind of bugs me. But and it's even worse if you're doing like a really quick random number thing. Like imagine a coin flip, right? So quick to execute. In that case, I guess because of having to hit some kind of global data for the seed, it's even slower. So it kind of bothers me, but as I say, as long as you are doing non-trivial operations inside of the function, it's fine. But if you are, don't use for each. The general procedure is you load the for each package, then you load your backend package, you register the backend, you call for each. How does the for each call look like? So you say library for each. Here we're in serial. I say for each I equal 1:3, and this has to be, no matter whatsies, on the same line as the %do. Okay, %do %. The reason is because just in the same way as if you said, say you have a matrix, when you do matrix multiplication, you say x %* %x, right? This is an operator, just like %* %. So if I just say for each I equal 1 to 3, it's going to spit out some nonsense at you. And then if you say %do %, after having done that, it's going to wonder what you're talking about. The R interpreter will not understand. So, and then inside of here you could imagine scope, you can add brackets, do all kinds of things, just it's a function evaluation essentially. So it's a really strange syntax for lapply as far as I'm concerned. But it is multi-platform, you register whatever backend, that is nice. When it works, it is nice. There are just some subtleties to be aware of. So another example, you could here, for example, I'm chopping up the work myself, basically, to do some kind of nonsense. It doesn't matter. Just some simple function evaluation. If you change %do % to %do par %, all of a sudden it goes from serial to parallel. And this is their canonical example they give, which would be really slow. But you say library for each, library my backend, and that would be any one of these things here. You register your backend using register, then uppercase D, lowercase o, uppercase, whatever the name of the backend is, some arguments for the thing, and you run it exactly the same way. So it's nice. In multi-core, you could say library do parallel register, do parallel note the casing. It's a little unusual. Cores equal to whatever in cores, I don't know. Then for each I equal 1 to 2, do par, get PID. For the Snow side of things with for each, you could do parallel, make cluster, register do parallel, you pass it the cluster, you do your stuff, and then you stop the cluster. Okay? So it's not a completely trivial change of syntax, but it's a lot closer than fiddling around with an MCL apply and a par lapply or cluster apply LB and all these different things available in Snow. So it's an option. It's available. The way it goes, make sure you register your backend, otherwise it will yell at you. Different backends may have different performance impacts. Do par for parallel. Do and do par must appear on the same line as the for each call. The function evaluation can appear on a second line, but that's just how the R interpreter evaluates operators. Any questions before we move to distributed computing for a very quick description of distributed computing? Okay, so most of our time spent discussing distributed computing will be tomorrow. But just very quickly, what is it? What are some options? So a node can only hold so much RAM. That number for, as I say, commodity hardware is about 32 to 64 gigabytes. That number grows by a factor of 10 or more if you have a lot of money in your pocket. But on commodity hardware, generally 32 to 64 gigabytes in RAM maximum, like physical limitation. With a few exceptions, those being FF and big memory and big analytics and so on. R does computations in memory, and as such, if your problem doesn't fit into the memory of one node, you need more than one node, right? Or maybe something like this is beneficial to you, but maybe not. One of the ways to break the cap of the memory available on one node is using more than one node. The packages for distributed computing parallelism in R, they include RMPI, and Snow can use RMPI. Exact same syntax, basically. You just register an MPI cluster instead of a socket cluster. There's Repay and RHadoop. RHadoop is really an ecosystem. Repay is a package. These live on top of Hadoop. Hadoop is non-trivial to install and maintain, but it may fit your problem, may not. Then there's PBDR, which we'll talk about tomorrow. Just super quick, what is MPI? Message passing interface. And remember that distributed machines can't directly manipulate the memory of other nodes. They can only directly manipulate the memory of the node that they live on. But they can indirectly manipulate them over the network. And that's what we use MPI for. We use it to pass messages over the network to tell the other node. It's like, imagine you really don't want to talk to your grad student, and so you just send them an email and say, hey, go do this. I can't directly control the manipulations of that person, but I can yell at him and threaten him and make him do what I want. And this is basically the same thing. So RMPI hello world, if we say mpi.spawn.rslaves and say with inslaves equal to 2, it's going to give me basically 2 workers. And once you do that, those 2 workers are going to slam your CPUs. You need to be aware of that. We've had some weird issues with that in the past. The nice thing about RMPI is that it is interactive. We have a different solution for MPI. It is not interactive, but it's got many improvements, I'll say. And we'll see them tomorrow. So I could say mpi.remote.exec. I am the mpi.com.rank. So the rank is, you have a communicator. Inside the communicator, all of the different MPI ranks, perhaps you map them one-to-one with cores, they're numbered 0 to the total number that there are minus 1. The total number that there are is mpi.com.size. If we execute this, it says I am 1 of 3, I am 2 of 3, because if you add 1 to these things. MPI exit, that will kill everything. MPI quit will just kill the whole R session and leave. Using RMPI from Snow, you could say make cluster with 2 workers, type equals MPI. You could also say make MPI cluster. And then, cluster call, par L apply, par S apply, all those things still work. They just now have an abstraction layer over RMPI, which is kind of nice. Stop cluster, MPI quit. So RMPI resources, there's a very small tutorial available. It's pretty good, but it's not super thorough. The RMPI manual is here, the reference page. Super quick PBD MPI versus RMPI. RMPI is interactive. PBD MPI is exclusively batch, meaning if you've used R script, we run it MPI run -np whatever R script and then a script, and then it runs and it's done, and you look at what it prints out. So coming from R, maybe that sounds really unfortunate, and we are wanting to move in the direction of having like a proper client server for interactivity. But to get something that's really good and scalable, you can't use the RMPI model, and that's why we don't use it. PBD MPI, however, is much easier to install, and we support Solaris, Linux, Mac. On CRAN, those binaries are available. Well, you install from source on Linux and Solaris. There's no binary for Windows available, but we do support it. It should work. One of our developers uses Windows, so he tests that extensively. The same is not true of RMPI. It's much harder. It can be made to work, but it's much harder. So PBD MPI also integrates with a bunch of other packages in an ecosystem. That's a benefit, I would say. PBD MPI has a much simpler interface. We'll see tomorrow. So some people, they say, well, who cares about the interface, right? In RMPI, you say mpi.allReduce, and that's an operation. We'll see tomorrow. Whatever it does doesn't matter. Type equals 1 for an integer. Type equals 2 for a double. You say, well, who cares, you say. Even though ours just looks like allReduce x. X is an int or a double, whatever. It doesn't matter. We just do the right thing. You say, well, who cares? Here's why you should care. Because R does crazy things like this. If you say 1, that's not an integer. If you say 2, that's not an integer. But 1:2 is an integer. And there's all kinds of weird stuff like this in R that you may not be aware of, and then your program crashes up on 200 nodes, and you scratch your head going, well, it worked before, what happened? So really weird things with data, translating an int to a double under the scenes. R does this all the time. And so why would you want to do that by hand? This is not C, this is R. R is supposed to be nice. This is our philosophy. And we'll see more of that tomorrow. But a quick summary, distributed parallelism is necessary when things don't fit in RAM on a single node anymore. You need multiple nodes. MPI is the de facto standard for that kind of thing. Hadoop exists. It solves some problems well. It solves a lot of problems not so well. Same could be said of MPI. But on large compute resources, MPI is the standard. We'll have plenty to say tomorrow. Several options are available beyond the scope of this talk. I have some exercises here. So maybe this was all completely trivial for you. Well, hopefully then you could take this back to somebody else who's working for you or with you, and you could have them look through this and look through some exercises. Here's one that Wei Chen prepared, which is an actual biology application with, I think, MCL apply. Yep. So you could work through it. It's completely self-contained. You would just need to read it and run it and understand it. And then I have some other, simple examples like do Monty Hall in parallel, these kinds of things. So those are available to you. Quick wrap up. So again, as I've said many times, distributed computing tomorrow. Compiled code with RCPP on Tuesday. We didn't talk about multi-threading because that's hard. You need compiled code anyway. We didn't talk about GPUs and mics because that's really hard. We didn't really talk about R plus Hadoop. That option exists. Maybe that's good for you. But that will wrap up the first session of high performance computing with R. Are there any questions? Sure.
What do you think about high performance computing with MATLAB?
High performance computing with MATLAB. What do I think about it? I have to be very careful how I phrase my response. I think MATLAB is very fast. I think MATLAB does a lot. It has a lot of neat toolboxes, like the SPMD toolbox. A lot of what we do is, I found out much later, is sort of similar to what the MATLAB SPMD toolbox does. They have a lot of support. It's also very expensive. They want to charge you like by the node. We ran our stuff up on 50,000 cores on Kraken, 4,000 nodes. Do you want to pay 4,000 MATLAB licenses? So that's basically my philosophy. The other issue is, of course, R is designed for data. I think R has a better syntactical, as much as people like to complain about R, and I'm in that category, R has a nice syntactical interface for thinking about data that I think it does it better than Julia, it does it better than MATLAB. So sometimes I think speed is very important, but then there are other considerations like money. And so. Does that answer the question? Yeah. OK. MATLAB is very fast, but the response that I usually give is it better be, it's expensive.
It does seem like it benchmarks slower than R for a lot of things. At least when I looked at the Julia benchmark, I was really surprised that MATLAB seemed
well,
worse than R in some cases.
there's usually like a toolbox that solves the problem better for you in MATLAB. It's kind of like in R, well, there's a package that does that. But those different toolboxes. I mean, you could compile the MATLAB stuff down to C, for example. There's a lot of really smart people who work on MATLAB. It's fast. It's a great product. I don't want to diminish that. But I prefer R. So
I think the thing that you're experiencing with the 4H is a well-known thing that has to do with the overhead time and why 4H is slow. So I'm wondering whether if you are going to use 4H, or actually how maybe you look into this when you get into PDR, about splitting up very large task lists. So like if I have, we do some analysis like a pairwise beta diversity, right? So we have 219 sites. So that's 219 times 218 divided by 2 independent comparisons. Each of them take 5 seconds, and so that's a really, really long time. And so thinking about how to break that up into a list is not trivial.
Sure.
So I'm wondering, and basically the reason I'm saying like that is if you were to, every 23,871 come combinations, if you were to put each of them to a for each loop, you'd see exactly what he showed, which is the fact that it's incredibly slow. So that you had 23,871 tasks, and they're redistributed back. How do you actually sort of solve that problem? Do you chunk it, just basically say 1,000?
Yes. So the solution to specifically, and let me know if I'm too specific, but the solution to specifically dealing with this for each issue where I wasn't aware it was well known, I'm glad it is, that basically when it forms this iterators object, right? And if you just give it too many tasks, it just basically, and if the tasks are comparatively slow, like if they take an hour, it's probably fine. If they take a couple seconds, it will be outrageously bad speed. The solution is to do this kind of thing here, and we sort of glossed over it, but the idea is you would divide it maybe into 1 to number of cores, and then give each core some set of tasks. And that's not entirely trivial. There are tools for doing that. Split indices could be helpful. As for what is most computationally beneficial, it sort of depends on the problem. I know I punt to that a lot, but it's true. Is that?
Yeah, because that's sort of the way forward. Is that like, of course it's slow, because basically what it's doing, right? In the naive sense, it's instantiating a new version of R. Like if you were to literally look at your task manager while you're running for each, you'll see the new versions of R popping up, and you're just not seeing them, like in the most literal sense of the word. And so the problem you're having is it's the overhead in instantiating a version of R, closing a version of R. I'm pretty sure that's actually what it is.
Well, it's more than that, because this was done with MCL apply, and I registered. OK, so here was with 24 cores. So I registered 24 cores with multi-core. Actually, I'm using the multi-core package here. So it's only spawning 24, if you like, different processes of R. There's an extra something in there that I don't quite understand that's gobbling up performance. It's in the iterators object creation.
So chunking alone won't actually solve the problem.
It should, as long as you're mapping to your resources fairly well.
Okay.
All right. Any other questions? We've run over a little bit. OK. Well, thank you very much.